Fragmentation in ethers.
The fragmentation of ethers is similar to that of alkyl chlorides, where it can undergo both heterolytic cleavage and homolytic cleavage. The carbon-oxygen bond is going to break heterolytically, while the carbon-carbon bond is going to break homolytically through the alpha cleavage. Now let's take 2-isopropoxybutane and find out the different fragments for it. First, we'll draw the molecular ion for this. Here is the molecular ion for 2-isopropoxybutane. Now in the first case, it's going to undergo heterolytic cleavage where both the electrons from the bond is going to go on to the oxygen. So here in this case, it has the ability to produce 2 carbocations. So if this bond breaks and both of those electrons is going to go on to oxygen, then it's going to put a positive charge on this carbon. So that would be 1 carbocation, but it can also break in the other direction where these 2 electrons are going to go onto this oxygen and it produces a different carbocation. Let's write down the different fragments. If this bond is the one that's going to break, then this is the carbocation that will be formed. This one has an M/Z value of 57. And if this is the bond that's going to break, you'll get an isopropyl cation. The isopropyl cation has an M/Z value of 43. So these are products of the heterolytic cleavage. Let's do the homolytic cleavage now. When it comes to homolytic cleavage, we are going to first find the alpha carbon. So for this compound, for this molecular ion, we do have 2 alpha carbons. Remember, alpha carbon is the carbon where the functional group is attached, or otherwise here where the oxygen is attached, right? So here we have 3 groups that can be eliminated. So basically, an ethyl radical can be eliminated, a methyl radical from here could be eliminated, or the methyl radical from here could be eliminated. So let's write down all the 3 possibilities and find out which one is going to be the most stable fragment. First, let's eliminate this ethyl radical by breaking this bond. So this is going to break homolytically. Remember, there are 2 electrons on it, and one of this is going to go form a double bond here, and the other one is going to go eliminate as an ethyl radical. So this is one fraction which has an M/Z value of 87. Let's also kick out this methyl group and find out what is the fragment that we'll be getting. So now we are going to break this bond. So this fragment has an M/Z value of 101 because you're losing a methyl group from this. So which means if I'm going to take that this one has an M/Z value of 116, the molecular ion has an M/Z value of 116. So when you subtract 15 from here, then it's going to be 101, right? So that's why you have, that's why this fragment is 101. Let's go on to the third alpha cleavage. Now we are going to remove this CH3. So if you remove this CH3, this bond is going to break. This is going to come in here. This unpaired electron is going to come here. So let's write down that fragment with the loss of methyl. So since here again there is a loss of methyl, this fragment is also going to be having M/Z value of 101. So now in the mass spectrum of this ether, you should have these peaks corresponding to these M/Z values. So first is the molecular ion, and then this carbocation, and then the isopropyl cation. And then there is going to be one peak for the M/Z value of 101. Let's take a look into the mass spectrum of this compound. So here is the mass spectrum. And yes, we do see a peak for 116 for the molecular ion. But remember, we also have the heavier isotope of oxygen, because of which you see a very tiny peak right there, which corresponds to the M+2 peak. And then both of these fragments are going to lie at 101, at an M/Z value of 101. And this peak at 87 is going to be the most major of all of these fractions. Why? Because when you compare the radicals that are formed, Between a primary radical and the methyl radical, obviously the primary radical is going to be more stable, and therefore this peak is going to have a slightly more intensity than the one at 101. And then apart from that, you also have a peak at 57, which corresponds to this secondary carbocation. And then the most prominent peak here is going to be the isopropyl cation, which is the base peak for this compound.